morning, everyone. So let me start by putting some context into why I'm here. People always ask me, people know the highly popular Amazon.com web application, and they always ask me what this has to do with silicon, DFT, and test. So at Amazon, we also have the AWS business, which is all about the cloud computing. And AWS is one of the largest cloud providers in the world. So we have lots of infrastructure, data centers, and hardware around the world, and we constantly designing, building, and shipping custom silicon units into those data centers. Yeah, so let me take you to a short journey of silicon innovation at AWS first. So we have three main product lines at AWS, and it all started with the AWS Nitro system, which is basically about a smart card that offloads the main server and runs various network-related and storage-related and security-related tasks to free up the server to run only the user's workloads. The other product that we have is the Graviton server. It's a homegrown AWS ARM-based Graviton server, which is very powerful and efficient, and it builds up an ecosystem very quickly. And the third product line we have is machine learning acceleration. So those who want to run cost-effective inference and training in the cloud can use those accelerators. So our typical chip would look like this. We have large chips with many cores and also many interfaces. You can see here DDR interfaces on the left and right sides. You can see PCI express lanes at the top and the bottom. So we typically have lots of I/O, and this is great for testing. We use those I/O to drive massive amounts of scan data into and out of the chip. But this design is quite old. It's a couple generations back in time. 2 years ago, we decided to go multi-die. And this is a hot topic. Just yesterday we had a great panel on this topic, and a lot has been said about it. I'm not going to get into the details of the motivation going die to die. I'm just saying for the fact that we are also doing that. But look what happened to our I/O that we so much enjoyed in the previous generation, that we have so many of them. Basically, all the DDR and the PCI I/O went away into the smaller dies, and in the center we are left with a large chip that has very few I/Os and has very low test bandwidth, but still it's quite large, and we need to drive a high volume of test data into it to test it. So at that point, we already knew about the SSN technology, and it was under development, and it was around the corner. So we thought it could really fit us, and this kind of design is good for this technology because, first of all, we have many identical cores here, and we could take advantage of the Ultra compare that that comes with SSN. And the other thing is that we have very few I/O. So SSN can run over any number of I/Os, as few as you may have, and seamlessly, so you don't need to worry about anything, and no complications around that. So we decided to build the SSN design into this chip in parallel with the regular scan design, and this way we would have, first of all, we would have a good fallback plan in case something doesn't work out, and second, we would we would be able to do a fair comparison between what SSN design can do and regular scan design can do, and this is what I'd like to share with you today. So let's take a closer look on this chip. So we have more than 400 cores here. We were able to stick 150 GPI into it. It's not bad, but it's definitely not the 1,000+ I/O that we used to have in the previous generations of the design. So first thing we did, we increased the chain length from 300 to 1500. And this is to reduce the amount of EDT channel inputs and outputs that we need to drive and observe in the chip, and try to manage it better with the few I/O that we have in this chip. Now, even after that, we would still have a large pin max, and we still have 23 different scan modes, or scan domains, test rounds, okay? So that would be 9 internal mode test rounds, and what's even worse, 14 external mode test rounds. So typically, external mode is something that you do on top of everything, and it's just a small pattern set that you create in one round and apply it. But in this case, we have, because usually for external mode test, what you need is just to control the wrappers, right? You don't need to control all your scan design. But in this case, we have so many cores, we have so many wrappers that we need to control to test those interfaces between the cores. And we have very few pins, so we weren't able to control all the wrappers together, and we had to break this problem up into smaller pieces and test those interfaces in smaller steps until we cover everything. So this is a tricky moment here, because it is, first of all, it's a lot of work. You need to understand your design very well. You need to know all the interfaces, not just the main ones that move the big data around, but also the small ones. Couple controls here and there that one core sends to another. You need to know all that. And of course, everything must be tested. So you need to make sure that every such small interface is covered, and that you do control all the active wrappers on this interface together, and it's covered by one of your pin max configurations. So this process is both time-consuming, and also there is a risk here of missing out on something and eventually end up with coverage loss, okay? So by the way, this problem does not exist with SSN, because with SSN, we always can control any number of cores, any number of wrappers with as few pins as you may have, and this problem just doesn't exist there. So another thing that we did, so 23 rounds of test is not great, and we tried to fight back on the test time by raising the scan shift frequency from 100 megahertz to 200 megahertz. So to do that, we installed a complex scheme of pipelines in the chip, and it's not just about intercepting those wires that travel long distances with registers. It's also about balancing all the pipelines to all the identical cores, because as you know, this is how pattern retargeting works. You need to have all your identical cores with the same number of pipeline stages to the I/O, and some cores are close to the I/O, while some others are far away, and you need to make all that balanced, and there's really a lot of work here, and I personally spent quite some time building all those pipelines and checking that everything works fine, and reaching timing closure at 200 megahertz. And I would really not want to do this ever again unless I have to, but fortunately with SSN, I don't have to do that anymore. So let's look at the SSN design in this chip. So here I show the data path, how it travels through this chip. So first of all, at the bottom part, we have the first ring of the SSN near the I/O, and from there we have the branches. We can reach into those columns one after the other, and this way cover everything. So what we have here, we have a single pin max configuration. We don't need to play with those pin maxes anymore. And we have natural pipelining. We don't need to worry about pipelines anymore and balancing, because everything is pipelined. Every scan host is already a pipeline stage. So you just have this short hops from one host to another host. And sometimes if you want, you can also install a pipeline. It's all automatic and easy. And the clock speeds are much, much higher because of those short hops. So here, almost for free, we got to, we achieved almost 400 megahertz very easily. Whereas with the legacy scan design, we had to work hard only to reach the 200 megahertz. Let's move on here. So the next thing I want to talk is the test power. And I want to start with a small example. This will be very useful for the next slides. So consider two cores. core A and core B, these are two identical cores, and assume that the SSN packet size is twice the bus width. So we need 2 bus clock cycles to load the full scan word in all the cores, and so that they could fire the shift strobe into the scan chains, right? So the shift is happening in every core just once in every 2 cycles. In this mode, the internal clock is divided by 2 from the bus clock. Now, both cores are identical. They receive the identical packet. They do exactly the same job, but they do this at a different point in time, right? So how different? This depends on the delay of the packet, how soon the packet will get from one core to another. In this case, core B will receive the packet 3 cycles later after core A, okay? And we deliberately put that small pipeline in between these 2 cores, and I will explain why. So 3 cycles delay, when we work in divide by 2 mode, this means that in the steady state shift, both cores are strobing shift every other cycle, but because the delay between them is 3 cycles, they will be doing that at different phases in time. So we have 2 active phases of the bus clock, and the core A will fire shift at the first phase, and the core B will fire shift at the second phase. So they will never, their shift clocks will never be aligned. They will always be interleaved. And this is very good for power, okay? Because half of your design is doing shift, while other half is not doing, and the other way, instead of everything firing shift at once. Now let's see what happens in our chip. So here I will shortly explain the plot, but let's focus on the left side first. So we run a bus clock at 300 megahertz, and we run the shift clock at 150 megahertz, again, because the packet size is twice the bus width. And also here, we create this situation with 2 active phases of the bus clock. And we do it in such a way that every 2 adjacent rows in this grid will never be aligned on their shift clock, okay? So basically, in this plot, you can see the current profile over time. And current is equivalent to power, just multiplied by the supply voltage, and you will get the dynamic power that your vector is generating. So you see here 4 bus clock cycles, okay? And each pair of bus clock cycles is equivalent to 1 shift cycle of the complete design, right? We have 2 phases, 2 bus clock cycles, and half of the design is shifting in the first bus clock cycle, and another half in the second bus clock cycle. So you see 6 peaks of current here, and each peak is corresponding to a specific row in the design. Okay, so in the first bus clock cycles, we see 3 peaks that correspond to the even rows, 0, 2, and 4. And in the second bus clock cycle, we see the peaks that correspond to the odd rows, 1, 3, and 5. So the point here is that by playing with the pipeline stages on the data path, we are able to spread out the edges of the shift clocks and make a smoother power profile generated by our vector, and this gives better power margins when we apply this test vector. Something else to note here is that, of course, when we look at odd cores or the even cores, and they all shift in the same bus clock cycle, but you still see a slight difference in time between those 3 rows. And this is because the clock also has propagation delay, right? So this also helps. But it's not something unique to SSN, it's always the case. So, but both of these 2 factors, the clock propagation delay and the phase we deliberately create between portions in the design help us create a smooth power profile and have better margins in power. So let's see how it looks in silicon. So here we compare, you see 2 shmoo plots. So on the x-axis, you see the frequency of the reference clock. These are at-speed test vectors that we apply. And on the y-axis, you see the minimum voltage required for the test vector to work properly. So you can see that at the same frequency, the vector of legacy scan with aligned shift and capture is actually requiring a higher voltage to work properly than the vector with the staggered capture in SSN. And this, despite the fact that the SSN would test the complete design, all the chip at once, 35 tiles plus more cores around them, while with the legacy scan design, we are testing here just one domain, the column that is enclosed with this white box that you're seeing there, just 7 tiles. This is all we test. And the minimum voltage required to apply that vector is even higher than what SSN requires for the complete chip. Okay, so this is a little bit counterintuitive because you kind of test more with less, but I hope you now understand why and how it happens. So let's talk a little bit about optimizations in the packet that help reduce test time. So here, so we have two things here. One is on-chip compare, and the other is throttling of the packet. So I show here first the full chip packet size before they enable the on-chip compare. So it is more than 2,000 bits. This is about all of the EDT channels that we need to drive and absorb in the chip. That's what this number stands for. So once we enable on-chip compare, and since we have many identical cores, that packet size shrinks dramatically to 355 bits because all those identical cores are sharing the same slots in the packet, both on the input side and the output side. So this is a great reduction of test volume. Next is the throttling optimization. So throttling optimization is about managing the bandwidth of each and every core in such a way that cores that have lots of test data, they will receive many slots in the packet, whereas cores with less test data will receive fewer slots in the packet because they have less work to do, so we can slow them down and make them work slowly. In the end, they will finish more or less about the same time when the big cores will finish with lots of work. So everything will finish more or less aligned, but our packet will become shorter, and we will send the same amount of packets, but the packet will become shorter, and eventually the test time will go down. So throttling optimization here reduces the packet further by 1.7x down to 204 bits. Let's talk a little bit about test time. So for reasons of confidentiality, of course, I cannot show you the actual test time of these parts, but I can show you the reductions that are resulting from moving from the legacy to SSN. So in terms of test cycles, we have reduction of 2.3x, and this is a result of packet throttling and on-chip compare, as I explained earlier. For the clock frequency, we also run faster with SSN, so it's another reduction in test time by 2.4x. So that adds up to total test time reduction of 5.5x, which is very nice. Okay, and remember, we put some effort to speed up the shift frequency of the legacy scan design. And had we not done that, the speed up would be even greater. So the folks on the test floor are very happy about it, and of course we reduced the operation costs, and test time is money. You all know about that. And this is what we achieved. So I will conclude with what benefits we have gained from the switch to SSN. So on the design, from the design perspective, we need to do less planning upfront, and we just converge quicker to RTL freeze milestone. We have less risk of test coverage loss because even when we have few pins and many cores and large wrappers, we don't need to deal with breaking those up into smaller interfaces and manually building that big puzzle from small pieces. So with SSN, we test normally all the interfaces in one round. We have more robustness. Our top-level design is more robust because usually any change inside the core is encapsulated inside the core. So if logic changes there and you need to fix your compression, you need to add or remove some EDT channel, those things do not reflect to the top level, okay? So at the top level, you still have the standard SSN bus. This is the interface of your core, and nothing changes at the top level. So the top level is more stable and robust, and all changes are within the cores. That's another great advantage from the design perspective. From test time reduction perspective, as I showed you, we have 5x even more, and this is a result of higher clock speed and on-chip compare and packet throttling. And from the power perspective, we saw that staggered shift and capture clocks help make the power profile generated by our vector milder, smoother, and we have better margins, and we can test more with less. So the concurrency of tests improves. So that's pretty much all, and I will end this talk with a quote from our founder, Jeff Bezos, that every new thing creates 2 new questions and 2 new opportunities. So clearly SSN has cost. Okay, you will need to put some effort to make it work in your design. You will have some obstacles that you will need to overcome, but at the same time, there are obvious advantages here, as you have seen in my presentation. So I really encourage you to explore this technology further and see what you and your design can benefit from it. So that concludes my talk. Thank you very much.